today's lecture is about SAT. And SAT is, satisfiability problem is probably the most important problem in all of complexity theory. So that's why we're going to spend a whole lecture and more talking about it. And actually, there are many problems about satisfiability, and I've listed just some of them here. And we're going to talk about all these problems today: circuit SAT, formula SAT, CNF SAT, K-SAT, 3-SAT. And that's a lot of problems, and there are more. And you may ask, am I really have to know about all these different problems? And the answer is yes. They're all very important, and so you must know about them. I've listed them here actually in order of most general to least general. Let me say more general to less general. So we're going to actually start talking about this one, circuit SAT, which is a very general problem. And particularly, that means for algorithms, it's quite hard. And formula SAT is a special case of circuit SAT, so it's potentially easier. And CNF is a special case of formula SAT, so it's potentially easier. And K-SAT is a family of problems, one for each number k. And these are special cases of CNF SAT, so they're potentially easier. And one particular choice of k is 3-SAT. So 3-SAT is a special case of all these problems, and so it's potentially easier. But still, it seems pretty hard. So that's exactly what we'll talk about in today's lecture. OK, so great. So I'm going to talk about all these problems. And so the first one on the list is this one, circuit SAT. So I think in most incarnations of 251, you talk about Boolean circuits. So probably you've seen these before, but I'll remind you, since they're also a very important topic for complexity, and we'll see them again in several subsequent lectures. Voila. So this is an example of a Boolean circuit, which I'll call C. And you've probably seen things that look a little bit like this before. So this is not 100% really a definition, but I'll just say some facts about Boolean circuits. So Boolean circuit C is something that looks like this. Well, it's a directed acyclic graph. OK, where the nodes, these inputs are also nodes. The nodes are called gates, and the edges are called wires. So you imagine it's actually implemented in reality. And usually it has n inputs called x1 through xn. Hold bits, true or false, 0 or 1. Usually you talk about 0 and 1 with circuits. So there's n equals 3 here. It has one output, which is this wire coming out of the top. Or you might think of it as this last circuit in the DAG order. And as I said, these vertices are called gates. So sometimes people allow different kinds of gates, but let's keep it simple and say we have and, or, and not gates. And these gates have what's called fan-in. Fan-in just means the number of inputs coming in. And sometimes in circuits, you let and or have as much fan-in as you want. But let's, again, just keep it simple and say these three kinds of gates have fan-in 2, 2, and 1, respectively. OK, so every and should have 2 inputs coming in. Every or should have 2 inputs coming in. Not inputs, I mean wires coming in. And every not gate should have 1 wire coming in. And we'll also use this term fan out, which is the number of wires coming out of a gate. Of gates. And this can be arbitrary. So you can have as many wires coming out of a gate as you want, which is convenient. If you think of this as doing some computation, it means you can kind of reuse a computation. See, once this circuit is computed x1 and x2, it feeds it in here, it feeds it in here. Well, it's got fan out too. You can have as much as you want. OK, so that's it's not a proper definition, but I think you all know what I mean. It's one of these things. And let's talk about, of course, why do you care about a Boolean circuit? You imagine it's doing some computation, that it takes in the n input bits and spits out an output bit in the obvious way. You compute the gates as you go up. And so really, you can think of C, a circuit. It computes a Boolean function. Okay, which maps n-bit strings into 1 bit. Okay, so here I'm using, I don't know, the convention 0 is false and 1 is true. You see, for any n-bit string you put at the input, you get 1 output bit. So it computes a function like that. And I'm going to do something that's like a little naughty notation-wise. I'm going to also call that function C. Really, that's a little bit bad notation because C is supposed to be the circuit, and the function is not the circuit itself is not the same as the function it computes. But eventually, it's just too annoying to write it any other way. Like I should really probably put like f sub c here or something, but I'm not going to do it. Hopefully, we'll all not get confused. Good. So actually, you can think of circuits as a computational a form of computational model, like Turing machines or programming languages and so forth. But they have like one weird aspect that's like different and like annoying compared to other programming languages. Somebody remember what that is? I know some of you know. Carolyn? Yeah, I mean, or another way to put it is like one circuit only operates on inputs of a fixed length. Right? A circuit like can only take, this one can only take 3-bit strings. So it cannot compute on inputs of length 4 or 2 or anything else. So that's annoying, and that's actually the main reason why we don't or one of the main reasons we don't use circuits as our first model of computation, even though they're quite simple and nice. So we'll probably talk about this issue again later, but in the class. But let me just not worry about it for now. Don't think about circuits as, necessarily a computational model. Just think of them, some object that you might build for some reason. Okay, so you can think of them as though as solving like a decision problem, but only on the strings of a fixed length. Okay. So actually, we're going to talk about a computational task where the input is itself a circuit. It's like a little bit weird, but hopefully it's OK. So like with graphs, when the input to an algorithm is a circuit, C, well, the representation of a circuit C. Like in graphs, we usually prefer not to measure the running time as a function of the number of bits in the representation of the input. That's like the default thing, to measure running time in terms of the number of bits in the representation of the input. But for circuits, we just prefer to use different parameters. For input to the circuit, it's a circuit like C. We usually measure running times in terms of 2 parameters. With graphs, it's usually n is the number of vertices and m is the number of edges. Here it's actually almost the same thing. N denotes the number of inputs, input gates. And m denotes the total number of gates. So it's actually not so often that you're running algorithms where the input is a circuit. But in those cases where it happens, you usually measure the running time in terms of n and m. And often I say this, oh, we're actually going to measure our running time in terms of these other parameters rather than the size of the input. But usually when I say that, in fact, I think hopefully always when I say that, these parameters will be like polynomially related to the size of the input, which is pleasant. So it means that if you only care about whether something is in polynomial time or not, whether you measure your running time in terms of the size of the input or these other parameters, it's the same thing. And that's the case here. So for example, n is always less than or equal to m, sort of by definition. And what do I want to say about m? That's less than or equal to the representation size of the circuit for sure, because you got to write down the circuit, you got to say at least one bit or something about each gate. So that's the reason for this. On the other hand, how could I, you have to think a little bit about representations here. But if you use like a reasonable representation for a circuit, what's an upper bound on the size of the representation as a function of m and n? Imagine a little bit how you'd sort of store a circuit. Yeah? No, I want like an upper bound on the size of the encoding as a function of like m and n. Yeah? M squared plus n. Yeah. So why m squared plus n?
Actually, I guess because it's not cyclic.
Yeah?
It's just n plus m.
N plus m? Well, it's a little bit more than that because, I mean, it's going to be, you have to like write some stuff for each gate. So what do you need to write for each gate? Yeah?
Maybe like preem, because you have to store just the inputs of each gate.
Right. So how are you going to store the inputs? Yeah?
Write down the number, like the index of that gate.
Okay. Which requires how much?
Log n bits.
Yeah. I mean, basically, you have to write down, if there are m gates, you have to write down, like, you'll call them like 1 through m or something, and like, you'll write down each one. And for each one, you have to either say the name of 2 gates, or if it's a NOT gate. Okay, so you'll have to maybe use like 2 bits to say whether it's an OR gate or an AND gate or a NOT gate. And you'll have to use some bits to say, like, what are the inputs? And what are the, to specify the inputs to this person, you have to say the name of this gate and the name of this gate. So there are m gates, so to write down like the name of a gate takes like log m bits. So for each of the m gates, you have to write down maybe, I don't know, 2 log m plus 2 bits or something. So, if you do this in a reasonable way, this will be order of m log m. Is it okay? So what this is saying is that, I mean, if you look at this, like m versus m log m, those are very close. So the representation size is somewhere between m and m log m. So if you've proved that your running time of your algorithm on this circuit is polynomial in m, that's the same as polynomial in this. So it's fine. And somehow it's more natural to use these parameters. Yep.
That kind of assumes that you're only like mapping each gate to like some other gate. But given that you have like infinite fan out, couldn't you just have something that kind of resembles like a strongly connected graph, where like you have just tons of fan out to like every possible other gate that like well exceeds that?
Well, you'll never have more wires than 2 times m, right? Because it's true that each gate can have lots of fan out, but each gate can only accept fan in too. It's a good point, though. I mean, it takes a little thought to see that. Yeah. Good. Yeah, and actually, I mean, if you're the kind of person that likes to allow your AND and OR gates to take in like more than 2 inputs, which is fine, then it's better to count the number of wires rather than the number of gates, because then you don't have a bound that like the number of wires is bounded by the number of gates times 2. OK, so what kind of crazy, function or problem would take a circuit as an input? I'll give you like kind of a warm-up problem that's like not too complicated. But actually, this problem is also very important for complexity theory, even though it's kind of simple looking. It's called circuit, not SAT, but eval. And this is a problem. I mean, it's here's the algorithmic task. You're like given the representation of a circuit and also an input. This is in 0, 1 to the n, where this has n inputs. Just what is, or output, c of x? That's the whole task. I give you a circuit and an input and say, what does it output? Or, maybe it's a little early. We should, get some practice in. Normally, this is actually a decision problem, really, because, right, the output is 1 bit. So one can also think of it as a language. And usually when you write this thing in capital letters, it's denoting a language. So you might think of this equivalently as all the pairs C and X such that C of X equals 1. So what, roughly speaking, is the computational complexity of this problem? In other words, like, if you're going to give an algorithm for this problem, about how much time would your basic algorithm run in? Yep.
Exponential of m.
Exponential of m. So what's your algorithm?
Well, I guess I would start at the output bits, take the two, I guess, inputs to that and treat them as completely separate, like distinct entities. And then I would understand that like it's at most splitting twice, like, and then most creating two separate subproblems. I guess you can kind of simplify that to some degree with some like dynamic programming algorithm, but you don't really get access to that in TM language.
Well, first of all, you can do whatever you want with Turing machines. I mean, you can compile pseudocode to Turing machines with at most, I don't know, some polynomial slowdown. So you can do that. But also, I think it's simpler than that. Yeah?
Like O of M?
You're probably like, yeah, probably O of M, actually. Let me start out by just saying, like, it's in polynomial time. Because, I mean, all you have to do, right, you get the input. Like, you get that this is like 0, 1, 0. So you just like go to this gate and like compute it, and now you know what its value is, and you compute the value of this gate and this gate and this gate and this gate, and then you know the answer. Okay, maybe that assumes that like somebody gave you the input graph in a somewhat helpful format. So I don't really want to get into those details, but I mean you can certainly do this problem in polynomial time. You just compute it. I mean, if you obviously like write a program that like takes the picture of a circuit and like an input and figures out what the output was, you would write a pretty normal algorithm and it would run in polynomial time. And in fact, yeah, I mean, it depends a little bit on like your model of computation, your model of counting steps. But like if you're like in kind of like the RAM model and you're like a serious algorithms person, then you can actually probably do this in time order m. Because roughly speaking, at a high level, I mean, you do like, kind of a little bit of work per gate to figure out, what its value is from its children gates. But I don't want to get like too obsessed about this because it depends a little bit on your model for counting pseudocode steps. Okay. So actually, I'm going to move on. But like, as I said, this actually, even though it's sort of a simple problem, it's quite important in complexity theory. One reason is this is the best, it is an equally good and let's say the best example of a problem that is in polynomial time, but we believe probably does not have a very efficient parallel algorithm. So it's an example of a problem that we believe is sort of inherently serial. Like even if I give you, so in terms of parallelism, this is a little side note, but I thought I'd say it at this point. In terms of parallelism, you might imagine, let's say I give you on n input strings a polynomial and n processors. Now can you solve the problem like super fast, like in polylogarithmic time? That's what you hope for out of a great parallel algorithm. And this circuit evaluation problem is like, for complexity reasons, one of the problems where we probably think that's not the case. That even if I give you polynomial processors, it's still going to take you like polynomial time. And somehow the inherent difficulty is that, OK, this is a simple looking circuit, but like for a circuit with n inputs, there could be a path from like the input to the output that's length n, for example. And it's very hard to imagine how you could use parallelism to help you for that. Like, I mean, you can try to like work on like that top gate, but I mean, it feels like there's nothing you can do until like you know what the values of its children are. So that was like a hand-wavy explanation, but like maybe towards the end of the class, we'll actually get into like some real complexity reasons why this is a problem that's probably not efficiently parallelizable. OK, that was a side comment, though. Let me get back to on track. We're talking about SAT today. So now I can tell you what is this problem, circuit SAT. This is circuit eval. Let me tell you about circuit SAT. Right, so circuit SAT. You're just given a circuit. And you have to find out, yes or no, is there an input x such that C of x equals 1. OK, if you want to think of it as a language, it's the language of all strings which are representations of circuits such that there exists x such that C of x is 1. OK, so I'll give you a circuit and ask, hey, is there any way you can make the circuit output 1? That's the circuit SAT problem. OK, so similarly to like what we were doing in the last lecture, I'm just going to say, well, we have an algorithms problem. Let's talk about first what is the brute force solution. So what is the brute force solution? Yes?
Try every possible combination of n inputs.
Yep, of which there are how many? Yeah. And then do what?
And then circuit eval.
Exactly, yeah, great. So try all 2 to the n x's. And, do this, algorithm for circuit eval. And see if you get 1. And if you do, then great, you can output yes. And if you cycle through all the 2 to the n x's and they all make the circuit 0, then you can output no. OK, so the time for this, well, I mean, it's 2 to the n times, if you want to get really excited, you could put m. Or, if you're just relaxed, you can just say 2 to the n times poly n. OK, basically 2 to the n time. Maybe even a little bit more than 2 to the n. OK, well, that's not so great. So, you might, again, ask, all right, maybe there's a smarter algorithm. And yeah, we don't know any smarter algorithm. That's the smartest algorithm we know. So you may ask, but on the other hand, you might ask, well, if we don't know any faster algorithm than that, it's very unlikely maybe that there's a polynomial time algorithm. We also don't know that. It could be, I doubt it, but it could be that there's actually a polynomial time algorithm for this. That'd be very surprising, but we don't know how to rule it out. And in fact, one thing that we're going to do for the next couple of weeks is talk about NP and NP completeness, which I know you've seen before, but we'll get into it in more depth. And one thing that's true is it's in P if and only if, well, this thing called P equals NP holds. Okay, which hopefully you actually remember from 251. But most people believe that this is not true, that P does not equal NP, which means that circuit SAT does not have a polynomial time algorithm. But whatever this P equals NP statement is, if you recall it, it's equivalent to whether or not this problem can be solved in polynomial time. And, OK, whatever, in 70 years or something, we haven't figured out an algorithm that's really faster than this, 2 to the n. So it doesn't seem like there's a polynomial time algorithm. But that's what we're going to talk about in great detail in the upcoming weeks. OK, any questions about that? OK, so well, we talked about circuit SAT. So now we're going to talk about formula SAT. This one's funny because this is the one that's also sometimes just called SAT. So if you see just SAT, it means formula SAT. There's really actually not that much to say about formula SAT that we haven't already said. Right. So formula SAT, aka SAT, same as circuit SAT, but it's about formulas. What is a formula? A formula is a circuit where all the fan outs are 1. OK, so it's a special kind of circuit. I wish I had the other board up here. There's no way to do it, right? OK. It's a special kind of circuit where all the fan outs are 1. And formulas usually, it's great. Formulas usually, well, sometimes you draw them like the circuit pictures. But it's also very common to just write them with symbols. OK, so an example formula looks like this. x1 and x2 and x2 or x3. Could be or negation of x1 and x2. Okay, actually, okay, I really want to see the picture now, so. Oh, I screwed up. Is there really no way to get this board and this board up at the same time? Damn it. Shoot. Well, anyway. Well, I can do this maybe. Aha. This is terrible. Well, anyway, this this formula is actually computing the same thing as this circuit, which nobody can see. But what you can see is, oh, what a fail. You know, if you want to make this circuit into a formula, right? Like this guy has fan out 2. So it's like, great, I computed x1 and x2 here, and I want to like use that twice. So in the circuit, you're just like, great, I'll put the wires out of it. But in like the formula, like you got to sort of write it down 2 times, which sort of makes the size of the representation like bigger. So these two things are computing the same function, but like it's like bigger to write this one down. Anyway. But it's, yeah?
Does there exist a Boolean circuit that requires exponential larger formula to represent?
Does there exist a Boolean circuit that requires an exponentially large formula to represent? Great question. Let me think. I should know the answer to this. I believe the answer is it's not known. There are definitely circuits that require like more than big O blow up to represent them as formulas. Like maybe you have a circuit of size order n, but like the smallest formula has size n cubed. That's definitely known. I think it's not known whether like there could be an exponential gap. Part of the problem being, you know, to ever prove something like that, you need to prove something like this function has like only exponential size formulas. And like a lot of things in complexity, like proving lower bounds like that is hard. Outstanding question. So actually, wait a minute. Hold on. No, I take it back in some sense. See, one thing you can do, right? You can always just do the obvious thing. I should have done it this way. You can always do the obvious thing, which is, you know, take your circuit, and then you're like, well, I'll just replace this with a copy of, like, I need it twice, so I'll just represent it with 2 copies of itself. So if you knew the fan out was always at most 2, then you probably at most square the size of the circuit when you're computing it to the formula, because you know you need to make this subcircuit like twice. But I guess since the fan outs can be like really big, like if this fan out potentially could be like n, we were talking about this. Even though overall the fan out, the sum of the fan outs is bounded by the size of the gates. I've really got into like a rabbit hole here. You know, if this circuit had this gate had fan out square root n, then like you need to make like square root n many copies of this. Oh, but that's okay. I take it back, right? I think you can just look, every gate, maybe it has like huge fan out, like maybe it has fan out m. But anyway, you should just be able to make m copies of this gate, which will blow up the size by polynomial. Okay, I'll have to think about it, but maybe you can do it. Let's think about it. Excellent question. Yeah, actually, I think now I take it back. I think you can like convert a circuit to a formula with at most polynomial blow up.
The problem is if every gate has fan out like m, and they are say polynomial in terms of n of that.
Yeah.
Will that cause a problem?
I guess not, right? Because if you work from the bottom up, right, then like if you work from the gates from the bottom up, like the bottommost gates, even if they have fan out m or n, whatever, you have to replace them with m or n copies. So that's blown up your circuit by a factor of m, maybe the first gate. And even if every subsequent circuit blows up your gate by your formula by a factor of m, there's only m gates, so you should do it at most m times. Oh, but that's bad. That's m to the m. Well, maybe I cannot resolve this on the spot.
Can only 2 gates be have fan out m though?
Yeah, that's the other thing. I mean, maybe you could work harder to say like, well, we know that the sum of the fan outs is at most 2 times the number of gates. Okay.
You have root n levels, and each level
Yeah.
feeds into every gate on the next level.
Yeah.
Then you get like root n to the root n.
Okay, maybe I take it back again. First instinct was right. Okay, great question. I'm going to look this up and get back to y'all. Good. Well, in any case, formula SAT is sort of a special case of circuit SAT. It's literally a special case because like it's the exact same problem, but you know, every formula is a circuit. Every formula is an example of a circuit. So this brute force algorithm for formula SAT still works just fine, order m times 2 to the n. Now, potentially it's easier, right? Because it's a special case of circuit SAT. But as it happens, we still don't know any algorithm better than this for formula SAT. Furthermore, it's still the case for formula SAT that it's NP complete, if you remember what that means. So it's in P if and only if P equals NP, which we think is unlikely. So somehow, even though formally it's easier than circuit SAT, we still know that like either they're both in polynomial time or they're both not in polynomial time. Probably both not in polynomial time. Yep.
But how can it be formally easier if they're both complete, though? Because wouldn't that mean if you can solve formula SAT, you can solve circuit SAT?
That's what we'll eventually show, that if you can solve formula SAT in polynomial time, then you can also solve circuit SAT in polynomial time. Which is not obvious because formula SAT is like an easier problem. Like you only have to worry about the circuits which are formulas. But still, you can do it. So that's what we'll see later. OK, great. So we did formula SAT. Now I'm going to talk about the next one, which is an even simpler form of formula SAT called CNF SAT. All right, what is CNF SAT? Further, a special case of formula SAT. Where the formulas have a very special structure. CNF is a weird acronym that was invented in like the 50s or something. Unfortunately, we got to deal with it. You're promised that not only is the input a formula, the formula is a big AND. Of things called clauses. What's a clause? A clause is a big OR of literals. Unfortunately, you are obliged to learn all this terminology. What's a literal? It's a variable or a negation of the variable. OK, so a CNF is a special kind of formula. It looks like a big AND of clauses, which themselves are ORs. OK, so an example, CNF, stands for conjunctive, normal, form, whatever. Might look like this, x1 or x2 or x3. Here I'm going to allow myself to like write ands and ors that are of more than two things. And x2 or not x7 or x10. I don't know why I'm copying this example from my notes since it's just a random example, but anyway. X1, oops, well, or x8. OK. So you know, this long example, I've drawn 3 clauses. You see each clause is like the OR of variable or its negation. That's a CNF. And once you get to writing CNFs, you've probably seen this before. I'm going to instead of writing like negation x7, I'm going to start writing overline x7. That just stands for the negation. OK, hopefully you've seen these things before. 251. OK, so that's like a special kind of formula. And so again, the problem could be formally easier. I mean, CNF SAT is going to be the problem, same problem. You're given one of these things. You're trying to ask, is there an assignment to the x1 through xn that makes the whole formula true? Which is the same as saying it should make each of the clauses true. It's kind of like a constraint satisfaction problem. Well, it is like a constraint satisfaction problem, like on your homework. Like these clauses are like the constraints, and you're trying to get each of them to be satisfied simultaneously. And this is also a little bit annoying, but like for CNF problems, we change the notation a little bit. N is still the number of variables, but we just say M is the number of clauses. So unfortunately, I have to keep changing notation because it's not quite the same thing, right? Like if you were to write this as a formula, you'd have to like break up these ORs into like a tree, and then you'd have to like count the number of gates, and like this would cost you 1, the negation, but sorry to always change notation, but like once you get down to CNF formulas, it's extremely standard to let M be the number of clauses. But again, it's polynomially related to the representation size of the CNF. Okay, any questions? So again, CNF SAT is like a potentially even easier problem. You're just given one of these formulas. You got to find out, is it satisfiable or not? So what do we know about it? Well, still exact same things. It's in exponential time. In fact, you can do it in time again. Something like 2 to the n times m. Basically, you cycle through all 2 to the n x's, and for each one, you have to like check each clause to see if there's at least one true literal in it. That's what you're trying to do, right? For each clause, hopefully there's at least one true literal. And you can check. And that's actually, it's not quite the fastest algorithm we know, but we don't really know one that's like essentially faster than that. And in particular, this problem is also NP complete. If you don't remember what that means, it's OK. We'll get to it. But it has the property that it's in P if and only if this thing called P equals NP, which, as we saw before, is like if and only if formula SAT is in P, if and only if circuit SAT is in P, etc. That's my crazy abbreviation for circuit, CKT. It's not even a K in circuit, but there it is. Right, so again, this is really a special case of circuit SAT, basically. So I mean, of course, the circuit SAT could be solved in polynomial time. This is a special case. You could also solve it in polynomial time. But actually, as we'll see, the more interesting thing is it goes backwards. Like even if you could solve this simpler problem in polynomial time, then actually you could use it as a subroutine to solve circuit SAT in polynomial time as well. So that's the cool aspect of NP completeness that we're going to get into. Like you actually show all these mystery problems that we don't know if they're in polynomial time or not. They're either all in polynomial time or none of them is in polynomial time, which is pretty cool because they're different problems, but the answer is the same. Yeah, so like I said in the first lecture, like this NP completeness, it reduces the number of questions but does not increase the number of answers. OK. All right, I'm going to go on. So CNF SAT, great. We did it. Now let me talk about KSAT. So KSAT is actually not one problem. Unlike the other ones of the list, circuit SAT, formula SAT, CNF 3SAT, those are all just languages. KSAT, it's just there's one for each K. So there's a problem called 3SAT, and a problem called 4SAT, and a problem called 5SAT, a problem called 2SAT, etc. OK, let's get rid of circuits. All right, so what is KSAT? Well, it's quite simple. KSAT is the special case of CNF SAT where all the clauses have, at most, K literals. Occasionally, you'll see exactly 3 literals, but like, let's say at most occasionally, you'll see exactly K literals, but let's say at most K literals. That's a better definition. OK, so for example, like so far, this guy could be an instance of 5SAT. I mean, it depends what's in these ... dots, but like this clause has 3 literals, this clause has 5 literals, this clause has, well, we don't know actually. Now it has 2 literals, etc. OK, so if I say like 5 sat, that's one particular decision problem. It's like it's the same problem, CNF sat, but I promise you every clause has at most 5 literals. So again, it's potentially easier, right? Because you don't have to worry about all CNF formulas, just the ones where every clause has at most 5 literals. So for example, the most famous example of k-sat is probably 3-sat. For reasons we'll see why 3-sat is maybe the most interesting of the k-sat problems. OK, so an example input might look like, I don't know. Well, here's an example of 3-sat input. So far, at least. OK, so just every clause has at most 3, and it's also OK to have 2. It's also OK to have 1. Right. Now, actually, once you get to, let's say, 3-sat, your life is even a bit more simple than it was previously in terms of notation. Because in 3-sat, without loss of generality, you can say that m is at most some function of n. So for 3-sat, how can I reasonably, without loss of generality, bound m? What's like the most m could be? Yeah? 3n? A little bit bigger than that. Yep. Little bit bigger than that. But almost. I mean, the point is, there's no point, if you're a 3-sat formula, in having the same clause more than once. Because 3-sat is like, you're trying to find an assignment that satisfies all the clauses. If you have like the same copy of the clause, it's pointless to you. I mean, you'll either satisfy both of them or neither of them. So how many different clauses, or what's an upper bound on the number of different clauses you can make? Okay, how about the number of clauses with exactly 3 literals? I like this answer, yeah, 8n cubed. So to answer the thing I was saying, if you want, how many clauses have exactly 3 literals? That's exactly, is it exactly? It's at most n choose 3 times 8, right? Because there's n choose 3 ways to choose 3 variables. But there's also, these can be literal. So each variable can be negated or not negated. So maybe you have like 2 times 2 times 2 choices. That's 8. Anyways, that's at most that. Yeah, one sec. And that's still actually not enough, because you're allowed to have clauses of size 2 and clauses of size 1. But you can just say, like, look, if you want to have a clause of size 2, you can just, it's like x1 or x2, you can just imagine that you had x2 twice. That's the same thing as x1 or x2. So there's like 2n literals that you could put here, 2n literals that you could put here, 2n literals that you could put here, so 8n cubed. It's actually overcounting a little because, anyway, it's at most 8n cubed. Yeah?
You were saying it was like bounded by n choose 3. That doesn't take into account if you have doubles.
Yeah, exactly. So I mean, you can't just say like n choose 3 because, maybe like plus n choose 2 times 4 plus n choose 1 times 2 or something. But anyway, it's at most, let's say let's like make our lives easier. It's order n cubed. And in general, for k-sat, there's no point in having m bigger than about n to the k, order n to the k. OK, so this means that m is bounded by n, some polynomial in n. So usually, we only worry about running time as a factor of n. Because anyway, if you put m into the mix, it would just change things by a polynomial. OK. All right, so that's k-sat. Let's say 3-sat. So let's do the thing we always do. Like, what is the brute force? Well, same as always. You can do it in time, poly n times 2 to the n. Just go through all the 2 to the n assignments. For each one, check if it satisfies all the clauses, which you can do in polynomial time. And it's also the case that, if you're interested, if it's in some smaller thing. We don't know if it's solvable in polynomial time. And even this one is in polynomial time if and only if this p equals np thing. So even though 3-SAT is like a special case of a special case of a special case of circuit SAT, a much more difficult problem, we know it's like at most harder by, in some sense, a polynomial amount. Like if you could solve even the special case 3-SAT on polynomial time, then you could solve the super complicated problem circuit SAT in polynomial time. So again, this is what we'll be talking about in future lectures. But now let me give you a little twist in life. 3-SAT does have an algorithm that's much better than brute force. Not much better like it's in polynomial time, but it's better, a lot better than 2 to the n. So you can solve 3-SAT in time, let me say 1.34 to the n. This was proved, this was basically proved by a person called Schoening in 1999. And in some sense, like a better version, in a way I'll say, it's Moser and Schieder in what, 2010 or something? So it's not, OK, it's not polynomial time. In fact, it's still exponential time. But it's like better, it's a lot better than 2 to the n. So for example, just if I were to invent the letter capital N to stand for 2 to the n, then the brute force algorithm is about capital N time. And this faster algorithm is about capital N to the 0.42 time. That's sort of good. It's like a polynomial speedup. It's like better than square root of like the brute force algorithm. So this kind of stuff is quite interesting to me and to other people, even though it's still an exponential time algorithm. We probably don't think you can get it all the way down to polynomial time, but something interesting is going on because you can get it a lot faster than brute force. In fact, I can actually show you the algorithm that does this. I cannot, in this lecture, prove it, but I can prove it in about one lecture, which I won't do. So voila, here it is. Now, this algorithm is a randomized algorithm. So it's not like the algorithms we've studied before. It's like you would need like a randomized coin flipping Turing machine to execute this algorithm. Now, towards the end of the class or lecture, even more, towards the end of the semester, we're actually going to talk about randomized algorithms, but we won't for a while. But anyway, you've seen them before, and like in general, it's not such a big deal to have a randomized algorithm. So actually, Schoening gave this exact algorithm and its analysis, and then these two people showed that you could make a deterministic version of this algorithm, which got the same results. So let's just look at it for a second. It's a very simple algorithm. And as I said, the analysis of why it works is even not that bad. It would take maybe one lecture to do it, which we won't. But so what does it do? So it gets as input a 3CNF formula. It's called walk set, because it sort of does a random walk. And it has a big loop that runs for basically 4/3 to the n steps, maybe 4/3 to the n times some little thing like n. So it tries an exponentially many times this inside of the loop. And what does the inside of the loop do? Picks a totally random assignment. I mean, it just guesses a completely random assignment. And it's like, I hope this works. So then it does like a little inside loop where it tries this assignment and a few others. So you see this loop goes for about n squared steps. I put in 100 times n squared just for safety. So what do you do in this inside loop? Well, first you just check if, like by a miracle, the assignment you picked at random satisfies the formula. And that's polynomial time. This part is, there's a little bit hiding in here, but you just have to, it's like the circuit eval problem for 3CNFs. You just take this formula that you guessed and see if it satisfies the assignment. If it does, you're like, amazing, it's satisfiable. Otherwise, now this is like the interesting part. What do? Otherwise, there's at least one clause that it did not satisfy. So you collect up all the clauses that it did not satisfy, and you pick one at random, uniformly at random. Call that C. And then this is the thing that's like a little bit non-obvious, but this is what you do. You look at that one clause, which has 3 literals appearing in it, or maybe less than 3 actually, but at most 3. And you pick one of the variables appearing in it at random. So maybe that was like x7 or something. And then you flip x's assignment on that variable, x7. If it was true, make it false. If it was false, make it true. So now you've got x, which is like a neighboring assignment. It's the same on all the variables except for this one that you kind of randomly picked. And you just see if that one worked. And if it doesn't, you flip one more variable in this way, see if that one works. And you do that for a small amount of time, n squared tries. And if in this is like the random walk part. And if in this inner loop, you never find a satisfying assignment, you're like, man, this x was terrible. Let me go back to the top of the big loop and start with an all new random x. And you do that big loop many times, but not as many as 2 to the n. You do it like 4/3 to the n times. And if all this work, which is about 4/3 n to the n times n squared times poly n, so it's just 4/3 to the n times polynomial in n. If after all that work, you still don't find a random assignment or a satisfying assignment, then you just kind of say, you know what, I think it's not satisfiable at all. So, any questions about that? As I said, I'm not going to prove why it works, but yeah.
Wait, so it always outputs the right answer?
No, so that's the thing. It does not always output the right answer. If it outputs yes, then you're like, that's the right answer. Because it only outputs yes when it genuinely found a satisfying assignment. If it outputs no, that's why I put a little question mark there. You're not sure. Like, it did a lot of work and did not find a satisfying assignment. So like the algorithm is guessing that it's not satisfiable, but that could be wrong. Maybe it is satisfiable, even though it didn't find one. But here is a theorem. I mean, this is OK, so the main work of this person who we're showing was to design this algorithm and prove this theorem, which is that if the input 3CNF is not satisfiable, wait a minute. Well, let me just say it like this. Well, I can write it like this. If it is satisfiable, the probability that the algorithm outputs no wrongly is very small. I could write less than 0.00001, but in fact, it's even smaller. Like, it goes to 0 as n goes to infinity. I didn't actually look it up what this is. In fact, you can probably make the probability of error exponentially small as a function of n. But let me just say it's like you can make it smaller than any prescribed amount. So this is what usually goes on with randomized algorithms. They have some very small chance of error. But for every input, the probability it gives the correct answer is in fact, exponentially close to 1. Let's say arbitrarily close to 1. And it runs in about 1.34 to the n time. OK, so I'm not actually going to say much more about this. You can prove this thing without an incredible amount of effort. These people, Moser and Cheater, actually improved it to a non-randomized algorithm, which always gives the correct answer in 1.34 to the n time. But I wanted to tell you about it just to say that these things are more interesting than they might appear at first. There is an algorithm that's much better than 2 to the n time. Well, better than 2 to the n time for 3SAT. In fact, allow me to tell you a few more things. Oh, wait. Let me keep this down here. Allow me to tell you a few more things. I mean, that was very specific to 3SAT. But actually, you can do an extremely similar thing for, let's say, 4SAT. So 4SAT is a harder problem, potentially, than 3SAT. Because in 4SAT, you're allowed to have a 3SAT input. I mean, it just says that every clause has at most 4 literals. So in particular, it could be that your input has every clause has at most 3 literals. So 4SAT is strictly harder than 3SAT. But you can still do a non-trivial thing for 4SAT. So here's a fact. 4SAT can be solved in time basically 1.5 to the n. OK, this is slightly bad notation, but for safety, let me say times polynomial in n. This is always like much smaller than the exponential factor, 1.5 to the n. So that's better than 2 to the n. 5-sat can be solved in time 1.6 to the n. Now you should guess the pattern. 6-sat can be solved in time something like 1.667 to the n. Okay, now can you guess the pattern? You want me to do 7? 7-sat. Ooh. 1.7 to, wait, 1. Well, anyway, I'm not going to do it. Maybe something like this? Not sure. Wow, it's not arithmetic. I thought you'd have some fun with it, though. Yeah?
Like it's 4/3, then it's 6/4. Like it's going up like an even number on the top. So
Yeah.
Like 7 is like, so it's like 6, 8, 10, 12. The next one's like 14/8.
Yeah, I don't promise I got the digits right here. It's k-sat. Yeah, it's you can do it in time 2 minus 2/k to the n times poly n. Okay, I think that's consistent with all these, except maybe the 7-sat I just guessed there. So actually, you know, for any fixed k, this is a little bit better than 2 to the n. That's kind of interesting. And it's funny also, right? Like if you give me a fixed k, I can do it a little bit faster than 2 to the n. But on the other hand, CNF-sat, don't really know how to do it faster than 2 to the n time. And in fact, I can tell you how to do this one. You just have to erase this and this and make this 2 minus 2/k. And you know, I won't prove it either, but like this algorithm works to give that fact. Any questions? Yep.
But aren't all, so can't you just rewrite any CNF-sat as a k-sat?
The question is, can you write any CNF-sat as a k-sat? You have two choices. If you just say like, well, this CNF-sat it's an instance of k-sat for some k. Like every CNF-sat instance is like an n-sat instance. So you can like put n here, but that's essentially not very helpful because 2 minus 2/n to the n, well, it's very close to, this is like approximately 1/e times 2 to the n or something. So it's basically still like 2 to the n. The other thing you can do is, as we'll see with NP completeness, there is a reduction that reduces CNF-sat in general to 3-sat. Trouble is it increases the number of variables. So like you could maybe reduce CNF-sat to 3-sat, but maybe on 100n variables, and then you could do the 4/3 to the n, but like now the new n is like 100 times the old n, which kind of ruins your improvement. It's a good question, though. Actually, this is not even the fastest known algorithm. I just wanted to tell you this. For k-sat, like Pudlak, Sachs, and Zane in 2008 gave an algorithm that runs in time. I'm going to be a little bit imprecise here, but it runs in time basically 2 to the 1 minus about pi squared over 6k times n, which is like a little bit better than this if you run the numbers. Okay. Any questions? Yeah.
How the heck do you get pi into it?
Yeah, it's very interesting. Yeah. Isn't complexity theory great? Yeah. I have something very interesting to say now, but I'm going to save it for next time just so I make sure I get through the lecture. But I'm going to say something interesting about this later, so remember all these facts for next Tuesday. All right. Now you might say there's one value of k that I have not talked about yet that's a very interesting value of k. It's 2. I did not yet talk about 2-sat. K equals 1 is not very interesting. 2-sat. Now, if you're like a smart aleck, you'd say, great, can I plug 2 into this? And then this is 2 minus 2 over 2, which is 1. So 1 to the n is 1. So polynomial n. Yes, you can. In fact, you can do it here. You can just make this 1 to the n, which is like crossing it out. And this algorithm actually works for 2-sat in polynomial time. But I'm going to show you a different polynomial time algorithm for 2-sat. But that's the last thing I want to do, is show you that 2-sat actually can be solved in polynomial time. OK, so finally we got to like a special enough case that like you can solve it in polynomial time. And I wanted to show it to you because, I mean, it's not obvious. And maybe it'll make you think a little bit that like, OK, yeah, these SAT problems look hard, but sometimes you can do it. So 2-sat is like simple enough that you can solve it in polynomial time. So this is the theorem. 2-sat is in P. OK, so let me just, so we have one to talk about. Let me give an example input. Looks like maybe this, x1 or x2. This one I do want to copy carefully. x1 or x3 bar. x1 bar or x2. x2 or x3. And x3 bar. Okay, I threw in one clause of length 1 there at the end. This is a very simple input, but this is the task. You get an input that looks like this with potentially n variables. And you want to know, is there a setting to the n variables that satisfies all the clauses? So again, you can try all 2 to the n possibilities for x and check. But there's a smarter thing you can do. OK, this algorithm's proof. Well, I'm not going to, I'll describe the proof to you here. Starts with a little observation that helps out, which is that if you have something that looks like x1 or x2, that's the same as not x1 implies x2. I'll help you remember some elementary logic from, I don't know, 151 concepts. Like, these are the same thing, right? This is basically saying, well, if x1 is true, it's OK. Otherwise, x2 better be true. Right? If you just prefer the truth table, right, it's like true, 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 false, false, true, false, false. My F's look like T's. That's not very good. True, 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 false. And if you think about it, it's like true, 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 false. OK, so this, an OR of size 2 is really the same if you negate one of these things as an implication. In fact, you can do it 2 different ways, right? x1 or x2 is the same as x2 or x1. So it's also equivalent to not x2 implies x1. So step 1 of the algorithm for 2-sat, you don't really have to do this step, but it's helpful mentally. It's just rewrite the input with these implies. And use both copies, like both equivalences. So for this example input, I would just imagine that it's literally the same as not x1 implies x2, and the other way, not x2 implies x1, and got to do it with this guy now. Not x1 implies not x3, and do it the other way. x3 implies x1, and dot, 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 dot. And I'm going to do it even with these ones, these clauses. So let me first say that I'll treat this as x3 bar or x3 bar. That's fine. And so I'm going to get the same thing here at the end. I'll get x3 implies x3 bar, and x3 implies x3 bar. Okay, so I'm just mentally going to say, you know what? Instead of clauses of size 2, let me think of these pairs of equivalent implications. This one looks a little bit funny, right? But this constraint, if you think of this constraint, it's just saying that x3 better be false. Right? Because if you plug in true, you get true implies false, which is false. But false implies true is OK. And that's the same as when we just had it as not x3, right? That's saying x3 had better be true, false. OK. Good. So the next step of the algorithm is also really a bit conceptual. You don't exactly do anything yet. But you just draw a graph which pictures this new version of the input. OK, so maybe step 2. Draw a directed graph with 2n vertices, one for each literal. That's a little bit subtle, but let's do it. One for each literal. And 2m directed edges. Call them arcs. One for each implication. So remember, I use m to denote the number of clauses in the original input. And when we converted them to implications, there's 2 for each. Some of them were repeated, but that's OK. So there's going to be 2m edges. So I will now try to draw this. x1 bar, x2, x2 bar, x3, x3 bar. This one's satisfiable, by the way. All right, here we go. Oh, shoot. Oh, man. OK, I'm probably going to get this wrong, and therefore it's all pointless. But OK, maybe I did that correctly. This is supposed to be the same as this. If I didn't do it right, you tell me. And so far, it's just representing the input graphically. But we're going to really think about it in terms of graphs. And at this stage, I want to make a key observation about this graph. It's a very simple observation, but it's just this. If Li to Lj is an edge, and let me pause to say that I write L to mean literal. So when I say Li, you should think of it means it's either a variable xi or not of xi. In this algorithm, there's no real difference. The algorithm doesn't do much different between a variable and its negation. So I often talk about literals. So if there's an edge from this literal to that literal, then there's also an edge, sort of like an antisymmetric edge, from Lj bar to Li bar. OK, so for example, in this graph, there's an edge from x1 to x2. And there's also an edge from x2 bar to x1 bar. And that's basically by construction, right? Whenever you put in an implication, you're at the same time putting in the opposite one. OK? So this is a property of the graph that we're going to use in the algorithm. Now, you see, this graph is helpful because it kind of tells you about the flow of implications that are implied by the constraints and the clauses in the input. You see, it's kind of easily shows you things suppose hypothetically that you were looking for satisfying an assignment where x2 was false. Maybe for some reason somebody said, consider x2 being false. which I'll prefer to think about as x2 bar being true. Then you say to yourself, like, OK, if x2 bar is true, you like sort of can follow the arrows. It means that x1 has to also be true, and x2 has to also be true. Which actually, I guess, is a contradiction, right? If x2 is false. But you see that you can like chain these arrows up into paths which are still correct implications or correct consequences of the input constraints. OK, so like x2 bar has an edge to x1, which has an edge to x2, which I'll sort of write like I'll say there's a path from x2 to eventually x2 bar to x2. And actually, this existence of this path tells us something. It tells us actually that if you're going to be an assignment that satisfies the input, x2 better be true. This is OK, but it just means x2 had better be true, right? That's the only way you can satisfy an implication like this. So this, in any satisfying assignment, if such exists, x2 had better be true. OK, so here's a basic observation we can make. Suppose you stare at this graph, and you notice, hey, there's a path from x2 also to x2 bar. I don't think there is in this graph, but hypothetically there might have been a path from x2 to x2 bar. And that would imply that in any satisfying assignment, x2 had better be false. And then you would get a contradiction. Like then you would see, aha, that means actually there cannot be a satisfying assignment because there would have to be a true, x2 would have to be true, and it would also have to be false. So I call like these two things maybe contradictory paths. So here's a claim 1, which I think is kind of clear, actually. Once you draw this graph, if for some I, there exists a path from xi, not necessarily an edge, but a path from xi to x bar, and there's also xi bar can reach xi, then the instance is unsatisfiable. Right, and I think I'll just explain that in words. This means xi would have to be false, but this means xi would have to be true. I call this, let me call these contradictory paths. And actually, this is something you can check for in polynomial time, right? I mean, we talked about the path problem on last lecture, where I give you a directed graph and two vertices, and I say, can you get from here to here in this graph? And like just checking, like if there is such a path, is an example of that problem from x2 to x2 bar. So you can check this in polynomial time, and you can check the opposite in polynomial time. And you can actually do this for all two n vertices, all in polynomial time. That just adds like a factor n slowdown. So what I'm saying here is, in polynomial time, you can check whether or not there exists any contradictory paths. And if you find contradictory paths, like x7 goes to x7 bar and also x7 bar goes to x7, it's unsatisfiable. You can just say unsat. You can say no. Is that OK? So the main point of the algorithm is that, and this is not obvious, if you don't find any contradictory paths, you can actually say yes. That's going to be claim 2. If there are no such pairs like this, it is satisfiable. That's not obvious, and like the main work is to prove that. But once we prove that, we're done. Okay, so this is claim 2. If there are no paths, the instance is satisfiable. Okay, once I prove this claim to you, then it finishes the proof that 2sat is in polynomial time. You just check to see if there are any contradictory paths. If so, then you could say no. If not, then you can say yes, it is satisfiable. Okay, so here's the proof. Hopefully you can do it in 4 minutes. So let's assume there's no contradictory paths. For all I, we don't have both xi goes to xi bar and xi bar goes to xi. It's OK if you have one of them. It's OK if you have neither of them. Like, we're assuming you don't have both of them. OK, and what we're actually going to do is we have to prove that the instance is satisfiable. I'm actually going to show you an algorithm that finds a satisfying assignment under this assumption. And there's, some parts of it are clear. Like, suppose you're looking around and you see that this path exists. Well, you better set xi to be false. And here, you better set it to be true. So sometimes, like when you're going around and you're looking for contradictory paths, and you're sort of at the same time in the back of your mind trying to construct a satisfying assignment, sometimes your hand is like a little bit forced. And in that case, you pretty much should just set the variable the way you have to. And actually, that implies that you have to set some more variables, like the successors of that variable in certain ways, and so forth. It's quite similar to one of the homework problems, actually. And then, sometimes actually you have like a choice. Maybe neither path exists. And in that case, it's actually going to be OK to set it either way. So here is an algorithm which finds a satisfying assignment under this hypothesis. Take any unassigned xi, and if there is no path from xi to xi bar to xi, we'll try setting xi to true. Then, let me continue here. Assign xi true. And assign li to be true for all nodes. Sorry, let me say lj. Lj reachable from xi. Right? Like, for example, if you assigned x1 to be true, you better set x2 to be true as well. I'm obviously not going to prove it, so let me just write down the algorithm, and we'll do it next time. And also, just naturally assign the negation of lj to be false for all these literals. Otherwise, I'm going to put an else here. If there is such a path, then there isn't the other kind of path. So else definitely there's no xi bar to xi path. And so now we're going to assign xi to be false. And we'll do sort of the other obvious things. And we'll repeat until all variables assigned. So next time we'll show, I mean, it's actually obvious from this algorithm. It'll eventually try to make an assignment. The thing that could go wrong is, in all these assignments, it might try to assign a variable true and also try to assign it false, which would be a problem. But we'll show that that can never happen. Okay, so next time, I'll remind you of this picture and this algorithm. And we'll take 5 minutes to prove that it actually finds the two-set assignment when there are no contradictory paths.